Hello, hello. Today we'll be looking at the evolution of nuclear weapons over time. First couple of principles. All nuclear weapons are fission weapons. Even fusion bombs use fission as part of their design. This means that they all use a supercritical mass of uranium or other transuranic elements. However, to store a bomb, you need to keep that in a subcritical arrangement. Otherwise, it explodes before it gets to the target. Thus, you must transition that material from being subcritical to supercritical at the desired time. This has its own series of constraints. If the critical insertion time, the time between being subcritical and being at your desired level of supercriticality, is slow, the bomb can begin to detonate in a barely supercritical state and fizzle, essentially leaving far more unreacted material than was originally intended. On the opposite side, since this critical mass is waiting for a neutron to trigger it, it can take too long to go off while waiting for a random neutron, and the bomb can fall apart before it starts to go off. This is because nuclear weapons achieve the short critical insertion times by using explosives. To demonstrate this, the most basic type of bomb is the gun type device, such as the Little Boy bomb. It uses two separate subcritical masses that are supercritical when combined and fires one out of a gun into the other, in essence. There are two common features that are also in Little Boy that are common in future designs as well that are important here. First, you have the tamper, which is a neutron reflecting material surrounding your reaction site. This reduces the amount of nuclear material needed. For instance, Little Boy was just barely supercritical if you looked at how much uranium you need in a sphere to reach supercriticality, but was well over that threshold due to surrounding the reaction site with a tamper. A neutron initiator also removes the issue of waiting for random neutrons by providing a source of neutrons. Little Boy and future bombs use a mix of beryllium and polonium, which are kept separate, and then as the device goes off, are mixed, which produces a large amount of neutrons via alpha radiation from the polonium reacting with the beryllium. This provides a bunch of extra neutrons, which help to ensure that the uranium or other material begins reacting exactly when you want it to. Gun type devices, however, are a little bit of a dead end. They can only be used with uranium, as transuranics will have isotopes in them that will cause a fizzle by pre-detonating the bomb. So instead, all other bombs use implosion, which is a shell of explosives around your uranium, plutonium, etc. core, which push it all together into one critical mass, aided by the pressure reducing the necessary amount for criticality. The ideal shape for a critical mass is a sphere, so implosion devices form the material into a sphere in the explosion. However, this does not necessarily mean that the explosion or the unexploded shell of plutonium or other material needs to be a sphere. A non-spherical mass combined with a non-spherical explosion, if correctly designed, can be used to create a spherical final mass. The next step in nuclear evolution is fusion boosting. Conventional fission bombs do not efficiently use their material even when they do not pre-detonate. The Fat Man bomb used only 20% of its plutonium, and the Little Boy used only around 2% of the uranium. Similar in concept to the neutron initiator previously described, adding fusion fuel, such as hydrogen isotopes, tritium and deuterium, provide a target for neutrons from the fission to create more neutrons than would be created by just fission reactions. which are then in turn fed back into the fission reaction, further boosting that process. A fusion boosted bomb is not a fusion bomb. It only around 10% of the energy comes from the fusion. It simply uses fusion to further enhance the fission explosion. Related to this is a sort of branch evolution is the neutron bomb. This uses a similar process of using a fission bomb to trigger lots of fusion, but instead of using those neutrons to boost fission, it uses them as the intended end goal, creating a large burst of neutron radiation that is the primary focus instead of the nuclear blast and fallout. This reduces the fallout and blast effects, and which has potential applications, though there aren't many in use. Now we get to the big boys, which is the thermonuclear bomb. This combines the concept of fusion pumped bombs with the implosion basic ideal by creating an implosion from a nuclear blast. You trigger one nuclear blast, and then the X-rays from that explosion are used to implode a second shell even more efficiently than conventional explosions would. This works because the X-rays from the initial blast are faster than the shock waves and explosion tearing the device apart. So this all happens in a very, very short period of time. This isn't actually limited to 2 stages, which is when things get somewhat absurd. The second stage, which is triggered from one nuclear blast, can then be used to trigger a third, even stronger shell of nuclear material to create an even larger blast. The largest nuclear device ever detonated, the Soviet Union Tsar Bomba, was 3 stages. This also leads into a brief discussion of how tampers can be more than just a neutron reflector, as U-238 is often used as the reflector, both for the shell in a thermonuclear bomb and just the tamper in other bombs. The U-238 will react when enough neutrons or other radiation is pumped into it. So as the blast goes off, the shell becomes part of the bomb. This can significantly improve the output. The Tsar Bomba's tamper was omitted to reduce its output because even the Soviet Union was somewhat concerned, and that almost halved the output from 50 being only 50 megatons instead of an estimated 100 megatons. Beyond that, we're sort of into the realm of not quite science fiction. The Star Wars project, no relation to the movie, during the Cold War, had the principle of X-ray lasers. In a similar idea to how thermonuclear bombs use X-ray lasers to trigger stuff before the explosion. Uses the X-rays from an explosion to trigger something before the explosion destroys the device. The X-rays from a nuclear blast can also be used to briefly power a laser. This can create a few very strong laser blasts from a emitter directly adjacent to your bomb. This was considered for use as shown in this image in space as a defense against against ballistic missiles, where the bomb pumped X-rays would be used to destroy incoming ballistic missiles. There's also the idea of antimatter. Antimatter is even more efficient at converting matter into energy than a nuclear reaction is. However, it is very, very rare. The human race creates very, very little of it. This leads me to think that it would likely be used in a boosting role, similar to how fusion pumped bombs work, with the antimatter being held somewhere in the bomb in a way that as the bomb goes off, the antimatter releases energy that is used to trigger further and or more efficient fission or fusion. Thank you.